Hi, in this demo video, we are going to look at a topic called process state transition diagram. Well, from the GATE exam perspective, and in general from the operating system subject perspective, as you know, process state transition diagram is one of the important topic. Many questions were asked in earlier papers based on process state transition diagram, and the process state transition diagram also assumes importance because of the reason that there are many other topics of operating system which are dependent on understanding of process state transition diagram. So in this small video, essentially we are going to look into what are the different states in which the process can be in during its lifetime, and what are the transitions that the process is going to make, particularly for multi-programmed preemptive based operating system. Okay, so that is the agenda of this topic. Hope you are going to ensure that you are going to understand it. So let's start. So let me write down here what are the various states of the process first. So process states. Well, before writing down what are the different states in which the process can be in during its lifetime, I would like to tell you, I would like to emphasize that process as such is a program in execution. We know that very well. And process as an ADT. So here let me just emphasize, process as an ADT, process as an abstract data type, is associated with several attributes, is associated with several attributes. Remember that always an abstract data type is associated with four important parameters. What are the parameters? Like we say, definition, then we have representation or implementation, or you can invariably say process structure, and then process operation, the operation that we carry out on the process, and the various state and the attributes of the process. Okay, so as an ADT, process is associated with a well-defined list of attributes. Like what are the some of the attributes of the process? So let me write down. From the identification perspective, we have process ID. You can say parent process ID, okay, and then you can even say group ID. The process may be associated with program counter, some general register set, is it not? General register set, holding the temporary values of the temporary results of the previous operations. Process may also be associated with some priority, and then the process would also be associated with state, process state. So this is what I'm going to focus on. What are the different states in which the process can be in during its lifetime? Okay, and then later we will see what are the various transitions which the process can make. So essentially, let me pen down here the various states in which the process can be in. States. But number one, the first state in which the process can be in is called new. So I'll write down shortly. I will tell you what exactly is the meaning of new state, what happens in new state. Then we have the second state called ready. Okay, I'll tell you what is ready means. And then we can have running. Okay, and then we even have block, which is also called wait. All right, new, ready, running, block, wait, and then you can say terminate. Then you can say terminate. These are the different states in which the process can be in during its lifetime. So essentially, very briefly, I will tell you what exactly happens in new state, and then we will see what are the various transitions. So new state, resource allocation takes place. Now what does that mean? See, when you load the program for execution, the process gets created. One of the important aspects of creation is resource allocation. Like for example, I have to allocate memory to the process. I have to associate some files with the process, right? I have to associate some IPC mechanisms if required for the process. So what all resources which are quite essential for starting the execution of the process, that happens in new state. Like for example, I would say some standard files are associated with process at the time of its creation. Like you say standard in, standard out, standard error. So like that, memory is allocated, other input output, and various other resources which are quite essential for starting its execution, that allocation takes place, resource allocation. Then what does ready mean? Ready means it is ready to run on CPU. It is all ready with the required resources, right? So it is ready to run or execute on CPU. In a multi-program environment, as you know, there can be many ready processes, right? So therefore, that is a ready process. And then we say run or running. The state of executing instructions onto CPU is called running. Executing instructions. I'm writing in short, hope you understand. Executing instructions on CPU is the state of execution on CPU. That state is called running, okay? And primarily what is important is block, also called wait. So this means the process generally gets blocked for input-output operations, okay? Or maybe sometime the process may also get blocked for the execution of system call. As you know, system call is a call to operating system for the requirement of some service. Operating system is a service provider, and our applications, our programs are service users. Users are service users of the operating system. So as such, whenever we need any operating system service from the user application, we have to activate or invoke the system call. So whenever the user process activate or invoke the system call, then essentially the running process will get blocked. So that is called block. Likewise, if the process needs some input-output operation, or if it requires any resource which is right now not available with it, then also it get blocked. So that is the meaning of block. Then finally, we have terminate. Terminate. Now this is nothing but the process has completed all its instructions. This is completion. Just rub it off. Okay. The state of completing the instructions. Completion. Okay. Now this completion may be a normal completion or abnormal completion. So let me write. This could be a normal completion or abnormal. Abnormal means, like for example, if it has executed an illegal instruction, if it has access and a memory location which is not in its scope or in its address space, that is called abnormal termination. So the completion may be a normal completion or abnormal completion. If the process is completing all its instructions, and then it has not executed an erroneous instruction, or it has not executed an illegal instruction, then that is called normal termination or normal completion. Abnormal is the case when it executes an instruction which is generally like a trap or generally an error prone instruction. So essentially this is the meaning of the different states: new, ready, running, block or wait, are also called, and then finally the terminate. So these are the various states, and the meaning of them I have written down in short. And then now in the next slide we will see what are the different states in which the process can be in during its lifetime. Okay, so here process state transition diagram, the real diagram comes, and hope you are going to understand it very well. So this is the first new state. I am representing the states by means of a oval as such, indicating the state in which the process can be in, and the transition that it makes whenever the process gets created. As I said, when the process is in new state, resources are getting allocated, the process is getting created from the program as such. So when it gets finally created, it will go to a state called ready. So simultaneously I will mark the transition here for your understanding. Okay, with a different ink I will mark the transition. So this is creation. I will write it creation, or I will say just created. The process got created. Means the essential resources which were needed for the process have been allocated. Now it is ready to run, ready to dispatch onto CPU, ready to run on CPU. Okay, there can be many ready processes. So essentially, whenever the CPU is idle, whenever this processor is idle, we take one ready process and then we dispatch it onto CPU. So whereupon the process will change its state to running. So what do we do? Come along. Okay. So among the ready processes, Among the many ready processes present here in the memory, the operating system is going to schedule one of the process, is going to select one of the ready process to run or execute onto CPU. Okay, so it starts executing its instructions on CPU. That state is called running state. Okay, so this transition, let us mark it as schedule. The act of making a selection, okay, act of making a selection of a process. Like I have 5 processes. I have to decide, I means the operating system. The operating system has to decide who is going to get run onto CPU. That event of making a selection of the process is called schedule. And the act of giving the control of CPU, action of giving the control of CPU to the process is called dispatch. That is called dispatch. Just like we say courier dispatch, is it not? Courier dispatch. So like that we say the act of giving the control of the CPU to the process is called dispatch. Means it has got the control of CPU. It has got the control of CPU. The process is running on CPU. It is executing instructions by fetching them from the memory and fetching the operands and executing it. Okay. Now what are the possible outcomes from the running state? What are the possible outcomes from running state? So maybe in some cases the running process may terminate, may complete all its instructions. It might have finished its execution. So therefore it is going to a transition called terminate. It is making a transition to a terminate state, Okay, let me write. So this state we call it as terminate. What is the reason for termination? We have already seen. It may be because of completion. Okay, so I will name this transition as completion. As I said earlier, the completion may be a normal completion or an abnormal termination. So whatever it is, so that is completion. What is the other possible outcomes from the running state? The other possible outcome from running state is the process may need to go for IO operation. So therefore, in that situation, the state of the process will change to block. As I said earlier, block is also called wait. Block is also called wait. So the requirement for the block, as I said, is maybe the process need to get blocked for IO operation, or maybe when it executes a system call. Is it not? Either IO operation or system call. So realize, come on, running, the process is running, right? Again, you can check, the process is running on CPU. If it need to perform IO operation, if it needs to execute any system call, so we immediately leave the CPU and go to a block state. It remains in the block. It is waiting for the IO operation to complete. It is waiting for the operating system to complete the IO operation. Is it not? So that is block or wait. Okay. And then when the process leave the CPU and get blocked, then operating system may schedule another process onto CPU. That's why the process who is in the block state, when it completes IO, when it completes the system call, then essentially where should the process go to? So what I'm saying, when the process is in block state, come on, understand this. When the process is in block or wait state, and if it finished the IO operation or finished the execution of system call, operating system has finished the IO operation on behalf of the process. Operating system has completed the system call for the block process. Where should the process go to? Kahan par jayega process? Where should it go to? It will go to ready state. Very good. It will go to ready state. It cannot come to running. It cannot come to running. Why? I'll tell you shortly. See here. Just now I said, when the process is running and needs IO operation or execute system call, it will get blocked. Thereupon leaving the CPU idle. The moment CPU becomes idle, then the another process will get scheduled by operating system onto CPU. Is it not? So therefore, the block process cannot go to running state. It will go to ready, saying that I'm ready to run again. I have completed my IO. I have completed the system call, required system call. Therefore, I'm ready to run. So therefore, it will go to ready state. And the transition will mark it like, this is called input output completion, or you can even say event satisfaction. The event for which it was blocked, is satisfied, is completed. Okay, is satisfied, that is, it is got completed. The event is what? IO, or the event is called system call. So that is satisfied, that is over. So the process will come back to ready state. Now before I continue further, okay, I have one basic question for you. I'll just put the question, you try to answer. Point number 1, there are 2 questions I would ask. Okay, interestingly, Number one. Now this process state transition diagram, I'll take the different thing. This process state transition diagram drawn so far is an illustration of, is a demonstration of which type of operating system. I mean, is it illustration of a uni-programmed operating system? I'm writing in short, uni-programmed. Or is it an illustration of multi-programmed operating system? This is what I'm asking you as a question. This process state transition diagram is illustrating the concept of a execution of a uni-programmed operating system or a multi-programmed operating system. Just realize this. If you know the concept of uni-programming, if you know the concept of multi-programming, just put some effort, right? And then you can try to understand and tell, is it illustration of uni-programmed or multi-programmed operating system? It's very simple. This is multi-programmed operating system. Why? Because in uni-programmed operating system, we will have only one program present in memory, we'll have only one process present in memory. Okay, so I cannot have ready state in uni-programmed operating system. So my dear aspirants, if you want to draw the diagram of a uni-programmed operating system, how does it look like? So let me show in short, how do the uni-programmed operating system diagram looks like, so that you should have clarity of understanding with regard to distinction between multi-programmed and uni-programmed. So in uni-programming, I will show in a very short way, all right? I'll write in short also. This is new state for uni-programmed, okay? So as soon as the process get created, it directly start running on CPU. I'm writing in short, please, hope you will understand. It start running. From running, it may get completed, so therefore it will go to terminate. It will go to terminate. So what is this? This is ready, right? A new created, all right? So it starts running on CPU, and this transition is completion. And from running, the process may get blocked, so therefore it will come to block state. All right? It will come to block state when it require IO. And when it leave the CPU for performing IO operation, the CPU is idle in uni-programmed operating system. I cannot schedule another program because the ability of the uni-programmed operating system is to hold only one program. And when the running process complete, when the process complete the IO operation, it will come back to running. This is a beauty, right? Generally people do not pay attention and go wrong. So this is the diagram. I'll highlight it. This is the diagram of a uni-programmed operating system. This is the process state transition diagram of a uni-programmed operating system. I will have only 1, 2, 3, 4 states. Whenever the running program needs to go for IO, it gets blocked. From block, it goes back to running. This is the conceptualization of a uni-programmed operating system. So therefore, this is really a multi-programmed based operating system. Hope you follow my point. So my first question is done. Definitely the diagram which I have shown you is a multi-programmed operating system. Now next question. As you know, multi-programming is of two types, or multi-programmed operating systems are of two types. Number one, preemptive, the other is non-preemptive. Okay, so here I'm writing. So let me rub off this. Yeah, so I'm writing in short multi-programming as MPR. So just now I told multi-programming is of two types. One is called non-preemptive. I'm writing in short, non-preemptive. NPR is non-preemptive, and the other is preemptive. This is a GATE question asked several times, so please understand that. Non-preemptive means no forceful deallocation. Mean the running program will not be forcibly deallocated. Nobody will force the process to leave the CPU. That is non-preemption. Preemption means forceful deallocation. Running program will be forcefully deallocated from CPU. Okay, so what could be the conditions for forceful deallocation? The conditions for forceful deallocation would be like time is over, like a high priority process might come, so that may force the running process to relinquish the control of CPU. That is forceful deallocation. So now the question is, having understood the concept of non-preemptive and preemptive, can you just put your effort and then try to look at the diagram? This is what I generally say, the application of the concept. The whole of GATE exam is based on application of concept. Knowing is not enough, you should apply. So here I'm going to make you understand give you the point, the meaning of application of concept. Many a times I observe while teaching that students know what is uniprogramming, what is multiprogramming, what is non-preemptive, what is preemptive, but eventually when a question is asked, generally they fail to apply the concept. So here is a simple and beautiful example to show you, illustrate to you the application of the concept, right? So is it preemptive or non-preemptive? When I asked this question in the class, many a times I found students fail to apply and go wrong, right? So here look at that. The process is running on CPU. There are two conditions in which the running program is leaving the CPU. One is when it complete and the other is when it go for IO operation. So these two conditions, my dear students, are nothing but non-preemptive conditions. Process is voluntarily leaving the CPU. Nobody is forcing the process to leave the CPU. It is voluntarily releasing the CPU, right? That means when it got completed, normal completion or abnormal, it is voluntary. And input output, that is also self initiation. Input output is a self initiation of the process. All right. So therefore, these two conditions are the only conditions available here, which is telling the process, which is indicating that basically this is non-preemptive. So this is non-preemptive execution. This is non-preemptive. Now the question is, major question is, if you want to transform this diagram, if you want to convert this diagram from non-preemptive to preemptive, listen to that. From non-preemptive, if I want to convert it to preemptive, then what should I do? That's a great question. What should I do? I don't need any extra state. Almost all the states have been covered here. All the states have been covered here. Okay. So what is that extra transition that I need to make so that the diagram, right, process state transition diagram gets converted from non-preemptive to preemptive? That's very simple. So realize that the process is running on CPU, right? And then we have somebody means here the operating system. The operating system would force the process to leave the CPU. Forceful deallocation is preemption. Forceful deallocation is preemption. Okay. So process is running on CPU. It is operating system is going to say that your time is up, you have to leave the CPU. Operating system is going to tell that maybe we have got a high priority process to get scheduled onto CPU, you have to leave the CPU. So in that case, where should the process make a transition to? One mark question. Process is running on CPU. Operating system is forcing it to leave the CPU. Where should the process go to? Should it go to terminate? Should it go to block? Or should it go to ready? Naturally, it should go to ready. Why? Because process is saying that I have not completed. Process is saying that I don't need any IO. There is no voluntary condition. Process is saying that, okay, I wanted to run, I wanted to continue my execution, but you are telling me to leave the CPU, so therefore I'm ready to run again. I'm ready to run again. So therefore, when it gets preempted, the process will come back to ready state. The process will come back to ready state. So this event, I will call it as preemption. I'm writing in short, preemption. Now, what are the parameters based on which preemption will happen? The parameters based on which that preemption may happen may be because of time. I'll say timer out. Or if not timer out, maybe because of priority. Maybe because of priority. Like that, there are other parameters also that can enforce preemption. So now the process will go to ready state. Now, my dear aspirants or my dear students, what I would like to tell you that this is a famous 5-state process state transition diagram, which is illustrating the working of or the execution of a preemptive based multi-programmed operating system. Preemptive based multi-programmed operating system like Unix, Linux, Windows, Mac. These are the different operating systems which are basically preemptive in nature. So this process state transition diagram is illustrating that aspect of preemptive based multi-programmed operating system. Here I would like to tell you one more important aspect with regard to this diagram, that you have to remember always that while the process is in ready state, while it is in running state, while it is in block state, it is always in main memory. It is always in main memory. So let me write that point here. Okay. So point number 1, while the process is in ready state or running, the very important point, generally people don't pay attention and go wrong. Ready, running or block states, it is in memory. It is in main memory, physical memory. You can say RAM. New means it is in the transition of coming into main memory. It has not yet been fully created. Termination means anyway it is leaving from memory, so we don't say it is really in main memory. As such, it is going out from memory. So I cannot say it is exactly in main memory. So it is resident in main memory when it is in ready state, running state, and block state. This is one important point you have to keep in mind. The second important point which you have to keep in mind very importantly from GATE exam perspective also, that in a multi-program, or I would write it like this. In a typical multi-program, I'm writing in short, hope you allow me and understand. In a typical multi-programmed operating system OS, there can be greater than or equal to. There can be more than one. One or more than one. We'll write one or more than one. There can be one or more than one ready process, ready and block process. Block process. What I'm trying to say, please understand from the concept of the process state transition diagram. The basic definition of multi-programmed operating system is that it can have many ready processes. The ability of the operating system to hold and manage multiple ready to run programs is multi-programming. So I can have many ready processes. I will write it like this: greater than or equal to 1. Okay, I'll write with a different tinge for clarity purpose. So there can be greater than or equal to 1, greater than or equal to 1 ready process. Sometime no ready process, all may be blocked. Okay, just for understanding purpose I'm saying. Likewise, I can have greater than or equal to 1 block process also, right? Greater than or equal to 0 also you can write, greater than or equal to 0 also you can write. But the basic definition of multi-programming is ability of the operating system to hold more than one program in memory is multi-programming. Sometimes it can happen, I may have 0 ready process because some may be running, one may be running and others may be blocked. So 0, or I can have many ready processes. Like that, if one process get blocked, another process runs and that fellow may also get blocked. So I can have many block processes. So greater than or equal to 0, greater than or equal to 0. So minimum ready will be 0, minimum block will be 0, maximum could be all ready, maximum block can be all block, quite possible. But here I would like to emphasize, if I have one CPU, if I have one core, one CPU, there can be only one running process maximum. One running process maximum. I cannot have more than one running. As you know, one CPU can run one process. One CPU can run one process. So that is the point I'm trying to make here. In a typical multi-programmed operating system environment, there can be one or more than one ready process. One or more than one ready process and one or more than one block process. And under the circumstances, so here I will write down again. With one CPU, there can be only one running process. Is it not? With one CPU, I cannot have more than one running process. One CPU can run one process. So that's what I'm trying to say. With one CPU, there can be only one running process. You can suppose, sir, if I have more than one CPU, I have 3 CPUs. Then definitely I can have 3 running processes. I can have 3 maximum running process. The golden rule is, the rule of thumb is 1:1. One CPU can run one process. So these are the essential highlights of the diagram. Again, I am re-emphasizing, while the process is in ready, running or block state, it is in main memory. Number 1, there can be many ready processes, including 0. There can be many block processes, including 0. And there can be one running process maximum at a time if I have one CPU. This is the important aspect of process state transition diagram. The last aspect with regard to process state transition diagram is that sometimes the operating system has to swap out, partially roll out, move out the process from memory onto disk, That is called process suspension. So sometimes the operating system has to suspend some of the partially completed processes from memory onto disk. So in that situation, the process has to go out from main memory onto disk And generally that is done due to for the reason of improving the degrading performance. So here in this demo lecture, it is not sufficient, time is not sufficient enough to tell you exactly what are those circumstantial situations where the process will have to go out from main memory onto disk. I would just tell only one point to complete the diagram, saying that the process can get suspended while it is in ready state, the process can get suspended while it is running state, and the process can also get suspended from block state. I'll show only one diagram from where suspension can be done. Like the most desirable state for suspension, I'll show suspension with a different thing altogether. Okay, so the most desirable state for suspending a process, perhaps you can say ready, because it is neither running on CPU nor it is getting nor it is waiting for some event to happen. So the most desirable state you can say for suspending a process is ready. So when I suspend a process from ready state, it will go to a state called suspend ready. It will go to a state called suspend ready, because it got suspended from ready state, suspend ready. Okay, and later, so this event, let us mark it, this event is called suspend, means it got moved out, it got rolled out from main memory onto disk. That is called suspend. It got rolled out from memory onto disk for performance reason. Like I don't have sufficient memory, I'm lacking with resources, system performance is degrading. The only option left over for operating system is to suspend some of the processes from main memory and say that I will put you on disk, later I will resume you back so that you can complete your execution. So that event is called resume. So when I resume the process back into memory, right, it will come back into ready state, and from ready state it will run again on CPU and complete its execution. So this event we will call it as resume. This event we'll call it as resume. So sometimes some authors call it as swap out, swap in. Some people say roll out, roll in, or some people say suspend and resume. All three are synonymous, so you can follow any convention. So dear students, the last point I would like to tell you to close this topic on process state transition diagram, that as long as the process is in ready state, running state and block state, it is in main memory. It is in main memory. There can be many ready processes, there can be many block processes. Maximum all processes can be in ready state initially, all processes can be in block state, quite possible if I have all IO bound processes. If I have one CPU, only one process can be running on CPU. So maximum ready can be all N, maximum block can be all N, and maximum running can be 1 if I have one CPU. Okay, minimum is 0. There may not be any ready process because one may be running, all may be block. There may not be any block, so minimum block is 0, right? Because all other may be in ready and one may be running on CPU. I can have such situations or such permutations and combinations. Okay, and last point is when the process gets suspended, when the process gets rolled out from main memory onto disk, right? That event is called suspension. Why do we need to suspend? As I told just now, suspension is done to improve the degrading performance. Perhaps I can add that point for your convention here. Maybe in the next slide I will write it. I'll write it for your convenience. Sometimes the operating system has to suspend some of the partially completed processes. Some of the partially completed processes. Those processes which have not fully completed their execution, partially completed processes. Okay, and the point which I would like to add, when the process gets suspended, it is moved out from memory onto disk. So this is generally due to degrading performance. Performance is degrading due to degrading performance. Performance of the system is degrading. So we have to bring the system back to normalcy. So for that reason we carry out the suspension. So please remember, suspension is not termination. Suspension is not block. Suspension is also forcible deallocation. Forcible deallocation. The process is forcibly going out. But the difference between the preemption, this preemption, look at the diagram. Look at the diagram, please. Here, this is also preemption. This is also preemption. This is also preemption. But this preemption is causing the process to go from main memory to disk. This preemption is causing the process to go from memory to memory. It will not move out from memory when it gets with regular preemption. It is not going out of memory, please. It is there in the main memory. Ready means it is there in memory. So suspension is also a forcible deallocation, but in fact it will deallocate the process from main memory onto disk. So this is the process state transition diagram. Hope the diagram, all aspects of the diagram are clear, and based on this, I am very sure all the PYQs of GATE which have been asked based on process state transition diagram, definitely you can work out. Okay, thanks.